Okay, so we're doing chapter 2, general biology, Bio131, and chapter 2 is the chemistry of life. So simply we're going to we'll be covering from the overview to the matter, to the atoms, to the chemical bonds. All of this will be covered, pH, and then we will go to the polymers, including carbohydrates, fats, proteins, and enzymes. But today we're doing the first part, which is the first 6 parts. So if you just think about it, what are you made of, what's your disk made of? Basically, we're talking about the structure now. So generally speaking, these definitions are very important to know. Okay, when we see definitions, matter, what's the matter? The matter is anything that occupies space and have a mass, not just occupy space. It has to have a mass, and we call that matter. Okay, like electrons. Electrons, they occupy a little space, but they do not have a mass. So we don't consider this a matter. So matter is occupy space, that's 1, have a mass, that's 2. And there are 3 different forms when we see a matter. It can be liquid, it can be solid, it can be gas, right? These are the 3 different forms. So just understand that generally speaking, as we speak right now, there are a lot of chemical reactions that are happening every single second throughout our entire life, 24/7 throughout our entire life. Right now, as we speak, there are a lot of reactions going on, and these reactions are called metabolism, and we will come to this point. The atoms are the smallest units that retain the properties of the matter. So we said the matter first, right? Atom is part of the matter. And how to say atoms, or what's the definition? Is it the smallest unit and you stop here? No, that's wrong. It's not the smallest unit. The smallest unit that retain all properties. Meaning, if I'm talking about sodium, hydrogen, and then I take 1 atom of hydrogen, I still call it hydrogen. This is the smallest unit, but you still call it hydrogen because it have the properties of hydrogen. What if I get smaller than that? Like inside the atom, I have protons, I have neutrons, I have electrons. No, that doesn't count. So the atom is the smallest unit plus, not enough, plus smallest unit plus retaining all the properties. When you put atoms together, you can make a molecule. Like here is an atom of hydrogen, here is another atom of hydrogen, here is another atom of hydrogen, or 2 or whatever, 2 or more. Now I'm making it molecule. Are we following? Yes. So what's the smallest? Atom. When you put atoms together, you're making molecule. Okay? Element is the basic structure that cannot be broken down. I cannot break down this structure. If I combine the individual elements that cannot be broken down, like sodium cannot be broken down, if I add different sodiums, it can be a compound. So if I add sodium atoms, it can be a compound. But I just mentioned that when I add atoms together, it will be a molecule. Is it a molecule or a compound? What's the difference? So molecule and compound are not the same thing. So if we just look at this first, here is sodium, an atom of sodium. I add to it an atom of chlorine. That will make a compound of sodium chloride. Okay? So is that a compound? It is a compound. Is it an element? Is it a molecule, I mean? It is also a molecule. What's the difference? Here's the difference. Molecules, yes?
Sorry, I was going to ask a question.
You wanted to ask a question?
No, answer it.
Oh, okay. So molecule and compound, both of them are atoms together. I get an atom, another atom, that will make molecule. Or I get an atom, another atom, put them together, it will be a compound. Is it a compound or molecule? Here is the answer. Molecule is any two or more atoms together, irrespective if these are the same type or not. Compound, it has to be different. Okay? So if I have one atom of hydrogen, another atom of hydrogen, two atoms now, do I have a molecule or a compound? A molecule. Can I call it a compound? No. If I have sodium and sodium, what do you call it? Molecule. What if I have sodium and chloride? And molecule too. Did we understand this? Two atoms together, is it a molecule or compound? If it is different, it's a compound. Whether it's different or not, it's a molecule. So all compounds are molecule, but not all molecules are compound. Did you understand that? Sodium and sodium is a molecule. Sodium and chloride is a molecule and a compound. But you cannot reverse it. Did we understand? So compound is, what's your clue here? Different. It has to be different. Sodium chloride, is that a molecular compound? Both of them. It's a molecular compound. Right? But sodium and sodium, is that a molecular compound? A molecule only. Can you call it a compound? No. What do you call H2? Molecular compound. Molecule. What you call H2O? Is it compound? It's both of them. As long as it's more than one atom, you can call it molecule. Okay? Did you understand the idea? Okay. So here is sodium and chloride. Together that will make a compound. So this is for the first part. Okay? Second part. We're talking about the reaction now. If I have two elements and I put them together to react together, and I will get a product, you call that a chemical reaction. The two or more that I put them together, this is called the reactant. The reactant. And what you end up getting at the end is called the product. Like this. Or let me make it even more simple. If I have two hydrogen and put oxygen on it, what I get? Huh? Water. So what do you call the hydrogen? Reactant. What do you call the oxygen? Reactant. What do you call the water? Product. Right? Here is another example. I have glucose. I add oxygen to it. That will give me water and carbon dioxide. What do you call the glucose? Reactant. What do you call the oxygen? Reactant. What do you call those?
Product.
Both of them. It doesn't have to be one. The products of the reaction. Okay? All these matter are classified, or objects are classified depending on different categories, but or different properties that we will talk about. But we put all elements in, all known elements into a periodic table. Are you familiar with the periodic table? Yeah, it's right here. So here is the periodic table, and this is a way to organize all the elements that we know. And as you see here, start from 1, that's hydrogen, and it's going like 1, 2, 3, 4, all the way until 103. This is the highest one, which is lithium. Okay? This is 103. And I will talk about what each one of those numbers means. But remember, you have the symbol in the middle, and number above and number under. And we will see what it means. But this is the periodic table, generally speaking. What's a periodic table? It's a table that arrange or organize all known elements, and it's going in ascending manner. So now look at this. You should be able to read this. Start with the C, and the C is the symbol of carbon. It's carbon, and you see a number on top and another number under. The number on top is called the atomic number. Definitions are extremely important. You need to know what's atomic number. Okay? The bottom part is atomic weight. What's atomic number and atomic weight? Very important to know. Okay? Basics. Atomic number is a number of protons. What does that mean? Do we know how the atom looks like?
Yes.
The atom is like this. You have the nucleus, and you have protons and neutrons. What charge are the protons?
Positive.
Positive. The P, they remind you with the P positive. P positive. N,
No charge. No charge.
neutral. Which is neutral. No charge means neutral, right?
Yes.
So the N is the first letter of neutral. The P means positive. Just to remember it. And then you have shells around. Here is the shell number 1, and here is shell number 2. And you can go, depending on the number of electrons, you can arrange 1, 2, 3, 4, 5, 6, whatever the number is. Okay? And each one of those shells is like the shells that you have at your house. I have this shell, and I can put 10 boxes of cereal, for example, and that's it. This is the maximum, right? And then I have another shelf that's bigger. I can take 20 boxes of cereal. So if you wanted to fill it out, I have 5. Okay, put it in the first one. I have another 5. Still put it in the first one, right? Now it's full. I have 12. Okay, I'll put 10 in the first shell, and the 2 will go to the next one. Is the next one full? Not yet. You can still add a lot, right? So you can add until you fill out the shell. The first one can take up to 2. The second one can take up to 8. And we will see the rest, but for now, what's atomic number and what's atomic weight? Atomic number is the number of protons that are positively charged. P goes with the P. The N goes with the N, right? So the number of protons in the atom is the atomic number. Atomic weight is protons plus neutrons, okay? Which is basically what you have inside this nucleus, right? This plus this. And why did you call it atomic weight? Because atomic weight is everything that have weight. What have weight? Neutrons have weight, protons have weight. How about electrons? Why don't you add the electrons? No, the electrons the weight is small enough that's negligible. We ignore it as if it doesn't exist. That's how small it is or how light it is. Okay? So what do you call protons only? It's positively charged, but what do you call the number of protons?
Atomic number.
Atomic number. And what do you call both of them? Because it's everything that have weight. Protons have weight, neutrons have weight. Is that clear? Okay. Now if you look at different elements or different atoms, different elements, you can have carbon, oxygen, hydrogen, nitrogen, but in your body or in any organism, and human is considered organism obviously, in any organism you have those 4 that you need to remember are the vast majority. This is the huge amount. The largest percentage is oxygen, carbon, hydrogen, nitrogen. You have to remember this. Okay, these are 4 that contribute together. This is 96.3. The vast majority of our body is one of those. Nitrogen is the last one. Nitrogen.
I got oxygen, carbon,
Hydrogen. Okay, so oxygen, carbon, hydrogen, nitrogen. Obviously, we're going down. Oxygen, 65%. It meaning 2/3. 2/3 of your body is oxygen. And then you go down carbon, hydrogen, and nitrogen. All of those 4 together, 96.3. The very small percentage that's remaining is everything else. So 3.7%. I'm not expecting you to remember all these numbers, by the way. Okay? I just want you to remember the names. What are the four major ones? The vast majority. Carbon, hydrogen, carbon, oxygen, hydrogen, nitrogen. Okay? This is four. So I want you to know the names. These are the major ones. What else beside that? We have calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Those 7 are 3.7, which is still a good amount. It's not that tiny. But look at this. Look at all of these. Something like boron and chromium, cobalt, copper, fluorine, like the fluorine that goes into our teeth. We need an extremely small amount, less than 1% for all of those combined. So we call those trace elements. Trace elements. So what are the trace elements? Trace elements are elements that are required in minuscule amounts. Minuscule amounts means extremely small amounts. Trace amounts. Okay? Did you get this? So these, you don't have to memorize all of this. Look at it. Have an idea about it. But you have to know what trace elements mean. Okay? Trace elements are elements that are needed in trace amounts. What trace amount? Very small amount. Minuscule. Minuscule is, all of them combined is less than or up to 0.1%. Not even 1%. So we call it trace elements. Did we get this? So the major part, the major four, you need to know it. The trace elements, you need to know what does it mean. And you can see some examples. Fluorine, copper, cobalt, chromium, all of these. If you at least remember fluorine, copper, okay, zinc, magnesium, and so on. So these are the major proportions. We have the major part, we have small amount of this, and we have trace amounts of this. So now you can take it from the atom and you go up, right? Atom, molecule, or compound, right? And then you go to organelle, and then you go to the cell, and so on, right? Until you go to the echo. If you add this, what we're talking about today, with the chapter 1, you can take it from the atom and even from the composition of the atom all the way until the ecosystem. Do you remember that?
Yes.
Sequence that we talked about before? Mm-hmm. Okay. So here is an example of nitrogen atom. And nitrogen atom is known to have 7 protons, 7 neutrons, and 7 electrons. And by default, the normal is that you have equal numbers of those. Sometimes you don't have an equal number, and that's not the ordinary or the regular atom. The regular atom is equal. Proton, neutron, electrons, equal. I have 10 electrons, so automatically I have 10 protons and 10 neutrons. Okay? 777, 999. This is normal. We have some variations that I will talk about, but by default, it should be equal. Are we following so far? Okay. So here is, if you look at this nitrogen, I have 7 protons and 7 neutrons and 7 electrons. Where are the protons and neutrons located?
Little, yeah.
In the nucleus inside, in the middle, right? And what is, can you tell me what's the atomic number for this? 7. And what's the atomic weight? 14. And I should have 7 electrons under normal circumstances, or this is the basic type, the normal type. We will have different variations that are called the isotopes. We'll talk about those.
Oh, yeah.
But here is the number of protons, and here is the number of neutrons. So if you're saying the number of protons, this is the atomic number. If you're asking both of them, this is the atomic weight. But what else does the protons mean? The protons determine the chemical element. The chemical element. Yeah. Meaning, if you change one of the protons, we're talking about something else. It's not the same element. Okay? So if I change the protons instead of 7, if I make it 9, we're talking about something else. Okay? 9 is fluoride or fluorine. I'm talking about something completely different. I'm talking about protons. Others, they can be different. And we're still talking about the same chemical element. Right? Yeah. So what cannot change? The protons. You cannot change the protons. If you change the protons number, I'm talking about something else. So what's the importance of the protons? It determines the chemical element. This is nitrogen, this is hydrogen, this is this and that. So how to tell? It's the number of protons. Didn't you just say that the number of protons and neutrons and electrons is the same? This is the normal type. There are other types that are called isotopes. It doesn't have to be exactly the same. The one thing that will never change, otherwise we call it something else, is the protons. How about the neutrons? The neutrons are going to determine something called isotopes. And here is what I mean. What's a normal nitrogen? 777, isn't it? This is normal nitrogen. Can I make it eight protons? No, this is not nitrogen anymore. So 7 protons. But what if I change the protons and make it 8? Neutrons. If I change the neutrons, protons are 7 and nitrogen is 777. Okay for this?
Yes.
Okay, I'm going to do the following. Still the protons are 7, but I'm going to add one more neutron. Is it still nitrogen?
Yes.
Yes, but this is called an isotope. Did you understand what's isotope? Well, what if I make it, instead of that, I make it 6, an isotope? Is it still nitrogen? Nitrogen isotope. It's not the ordinary nitrogen. It's a nitrogen isotope. So what's the importance of neutrons? Determine the type of isotope. Okay? So each element can have different isotopes. And you only change what? Neutrons only. Can you change protons? You're talking about another element. How about electrons? Electrons are negatively charged. Okay, and it's the regular type, the normal type that we always talk about is 777. So the last 7 is referring to the electrons, right? The electron should be 7 as well. It is a negative charge, and it will determine the atom's ion state and chemical reactivity. And here is what I mean by this. If this is, just to make it easier, if this is the nitrogen that we just talked about, it should be 777, right? 7 means how many can this shell take? 2. So I put 2 here. How much is left? 5. It's the total is 7. How much is left?
5.
I'll put the 5 in shell number 2, right? Okay, so how much that the second shelf needs to be full? 3 more. 3 more. As long as the outer shell is not full, it's called unstable or reactive. Unstable or reactive. Okay? If it is full, it's stable and not reactive. Did you understand this?
Yeah.
So is the nitrogen reactive?
No.
How many you have here?
5.
Is it full?
No.
So is it stable or unstable?
Unstable.
Unstable and reactive. Unstable, reactive. If it is stable, it's not reactive, right? What if we're talking about ions? What do you mean by ions? Ions is, did we just mention that the number of positives is normally the same as the number of negatives?
Yes.
And even the same as the neutrons? I'm talking about the normal type now, right? 777. What if I removed one of the 7?
The electrons?
One of the electrons. Is it the positives and negatives will be equally?
No.
It will not be equal, right?
Yeah.
It will be more what? Positive or negative? Positive. I call that the positive ion. Did you get the idea?
When you give an electron,
What if I added an electron to that? Which one will become more negative or positive?
negative.
I call that the negative ion. Did you understand what ion means?
Yeah.
This is simply what it is. Okay? And do not confuse that with isotopes. Okay?
Okay.
Ions is something and isotopes is something else. Isotopes, same protons, but nitrogen is different. Okay? Ions, proton and neutrons are the same. The electrons are different. You either take one, not necessarily one, you can take more. But in all cases, if you take one, it will become positive ion. If you add to the normal number, if you add one, it will become negative ion. Okay? And that explain, if you see like K, and you see positive beside it, I'm talking about the ion of K, the ion of potassium. Is positive. What does it mean?
It's missing an electron.
Missing electron. It lost, right? It donated. Does that make sense so far?
Yeah.
So electrons determine two things. Number one, determine the ion. Is that an ion or not? Is that the same number, or you lost or gained? So that will determine the type of ion, right? This is the first importance of the electrons. Second importance is chemical reactivity. Are you full or not? Is the outer shell full or not? Yes.
How are we supposed to know, like, how many, like, your shells? How many?
You take the number. It will take 2, 8, 18. The next should be also 18. Depend on from textbook to textbook, but I will stick with the first 3 only. I don't want you to know more than that. 2, 8, 18. Okay. So you can make the math. If I told you like 15, can you tell me how to arrange?
Yeah.
2,
8, 5.
2, 8, 5. Right? Yes.
No. No.
No, it's 2, 8, 18. Okay? Sometimes there is no 10. Sometimes they say 2, 8, 8, 18. I don't know what are the variations coming from, but we will stick with 2, 8, 18. Okay?
There's actually a formula for it.
There is a formula for it?
2n squared.
So what would be the so 2?
N squared. So n is the number of shells there are.
Oh, okay. So there is a formula for it.
Yes.
Okay. So I will stick with the simple numbers, and I'm not asking you more than that. Okay, just the simple numbers. Talking about 7, 10, 12, something like this. Okay. So what are the isotopes? Isotopes are different in the number of neutrons. This will give us the isotopes. What's going to change if this is an isotope? The isotope is less stable. Okay, if you lost some of the neutrons, you are less stable, and it's going to decay over time, giving you radiation, and this is what they use in the nuclear reactors. Okay, this is what they use. They do not use the normal type. They get isotopes because the isotopes, they kick out a neutron or two or add or something. They play with the neutrons. So now you don't have the actual or the normal type. You have an isotope. What's the issue with the isotope? It's not stable anymore. If I have the number that's equal, 7 protons and 7 neutrons, that's stable enough, and it will not decay. You can leave it for thousands of years, it will stay as it is. While if you play with the neutrons, you're getting an isotope that's not stable anymore. It's going to start to emit radiations, and this is the theory behind nuclear reactors. That's not our issue now. I'm just giving you the idea what is unique about isotopes, beside the idea of having different types of neutrons. Okay? So now we're going to the ions, and I talked about it. If you gain electrons, you become what kind of ion? Negative ion. If you lose electrons, positive ions. Next part is about the bonds. Now let me say it this way, simply. Hydrogen, I'm telling you, it's one only. What one mean?
One proton,
One proton, one neutron, and one electron. This is normal, right? I'm not talking about
Actually,
the
no,
isotopes.
there's 0 neutrons. 0 neutrons.
Zero what?
Never mind.
No, what did you say? So it's 1, 1, 1, okay? 1, 1, 1. So how many did you put in the outer shell? Which is the first shell actually, isn't it? You're using one shell only. What do you have in the first shell? How many?
1.
1. Is it full?
No.
So it's reactive? It's unstable? What does that mean? It means it will try to find something else to react with. It's not satisfied. I'm not satisfied. I need my shell to be full. It's not full. I'm not satisfied. I'm not stable. I'm reactive. I will try to react with something else. Why are you doing that? To get my shell full. And this is my goal. I will try to react or look for something else until we together make the outer shell full. So this is one hydrogen. Hydrogen have one electron at the outside. Is the outer shell full? No? How many do you need?
One more.
One more. Here is another hydrogen. Same thing? How about if we share together?
The molecule.
Now it become a molecule. Is it a compound?
No.
No, it's not. It's a molecule, right? And we're sharing together. So you're not going to donate your electron to me. We are just sharing. Okay? Like I consider you electron with me, so you go together like this. Okay? So I have 2 electrons and I have 2 electrons. We are both okay. We are both good. We are both stable now, right?
Right.
I'm stable. I'm satisfied. I'm okay. As long as we're sharing together. So what kind of bond is this when we share? This is called covalent bond. Covalent bond. Okay? So this is one. We're sharing one. Can we share more than one? Yes. How about oxygen? Oxygen is 8. Okay? 8 means how many do you put in the first shell?
2.
And how many in the second shell?
6.
Is the outer shell full?
No.
No, there's still 2 more.
You need 2, right? Is it stable?
No.
Is it reactive?
Yes.
It is reactive. How many electrons are you looking for?
2.
2, right? So here's what I can do. If you don't mind, he's oxygen and I'm oxygen, okay? If I shared one, is that okay? Is that enough?
No.
No. How about I can share another one?
Okay.
Right? So now we're sharing 2. But are we both okay now?
Yeah.
Yes. Here is the thing. As long as we're sharing, we're both fine. If I detach myself, I will become unstable again.
Right.
Okay? So that, because of that, I have this kind of bond is very strong. Because you know that you cannot be by yourself. You have to stay. So this is the strongest type of bond. We call it the covalent bond. Co means together, isn't it? Co means together. So covalent bond is the strongest type of bond. And this is the depend on sharing. Did you lose anything? Did I lose? Did he lose?
No.
No, we're sharing. And we're all okay. Because I shared 2 with him. So my outer shell is fine and his outer shell is fine. Both of us are fine and we're not going to separate. I need him and he needs me. So this is the strongest type of bond. And this is the first type that we call it covalent bond. Second type of bond is called ionic bond. And when you think about it, this is the medium type, not the strongest. What's the strongest?
Covalent.
Which is sharing, isn't it? This is the strongest. The second, which is medium, average, and this is called the ionic type. And from the name, ionic means ion, doesn't it?
Yes.
So ions means you either lost or gained, right? So if this is sodium, and sodium lost an electron, it becomes a sodium ion now, not a sodium atom, right? A sodium ion, isn't it? And is that this sodium ion is positive or negative? Positive. What if I get a chlorine right beside it, and I give it that electron that I take from the sodium? The chlorine is going to receive. So what will be the charge? Negative. You call it negative chlorine ion. Did you understand? So now I have negative. Are you following so far? So now I have positively charged sodium ion, negatively charged chlorine ion. Because one is positive and the other one is negative, there will be an attraction between them, like a magnetic attraction, right? Positive and negative, they come together. They stay reasonably average, not as strong as sharing, isn't it? Like we can separate, we just attracted, we're not bound to each other, we're not sharing. We can separate, but so the point here is ionic bond is a bond between two ions, and they stay together because of attraction between positive and negative, and this is average. The third one will be the weakest one that's coming. So here are the chemical bonds. Covalent is sharing, ionic is transfer. And we have a little bit more to talk about the covalent bond. But if you just look at this, this is 11 and this is 17. This is sodium and chlorine. You lose one, you become positive. You gain one for electron, you become negative. They get attracted to each other. And what kind of bond is that? What kind of bond? Ionic bond. Okay. Now just adding a little bit to the covalent bond. Okay. In that example that I gave you, when I am hydrogen and he's hydrogen, if we're sharing one, is that okay?
Yeah.
Hydrogen, yeah, we're fine, right? What if we share two?
It's better.
First of all, we're both fine. Like I gave you example of oxygen with oxygen, right? Here is what you should notice. Number one, the first type is called single covalent bond because we share one, we make one bond only. One electron for me, one electron for sharing one. Single covalent bond. If we're sharing two, like oxygen, right? Oxygen, we're sharing two. Double covalent bond. Is that okay so far?
Yep.
Here is one thing. But here is what you noticed. I give you an example that both of us are hydrogen, or both of us are oxygen. So I'm sharing two and he's sharing two, right? Make sense so far? Here's another example. I don't know if you can get that or not. I have oxygen, and he's hydrogen, he's hydrogen. Now we're different. How many do I need? Two.
Two hydrogen.
Oxygen. He needs one. So I will do this. It's fine. Am I fine?
No.
No. Another hydrogen will come and we will share like this. I'm fine now. And he's fine and he's fine, right? But did we share equally?
No.
No, I'm sharing two, they are sharing one. Okay? When you share more, you become relatively, not negative, it's not an ion. Not an ion. When you share more, you get a little bit of negative charge. A little bit. Very weak. Okay? So I will become slightly, not that like the ion, slightly negative because I'm sharing more. And he's sharing less, he becomes slightly positive. So here's what's happening. Are we following? What I was talking about right now, oxygen and two hydrogen. What is this?
Water.
H2O, which is
Water.
water. Same thing here. Your oxygen, hydrogen, hydrogen. Okay? You did the covalent bond. You're sharing 2, 1, 1. Is that an equal sharing?
No.
It's not an equal sharing, right? It's not equal sharing. We call it polar. Polar. Because you have a pool. One is cooler than the other. I call that polar. So here's a molecule of water. And here's another molecule of water, right? You are slightly negative, right? And he's slightly positive, right? The hydrogen would slightly attract to the oxygen. A little bit. We call that hydrogen bond because of that slight difference. So I call that the hydrogen bond, and this is the weakest of all. The weakest one. Did you understand this? Do you understand what hydrogen bond means? So your hydrogen bond is going to share, to be attracted to her a little bit. A little bit. So this is the weakest of all. If you just add a little bit of heat, this bond is going to separate very easy. Just put it a little bit on heat, it's gone. This is how weak it is. So the hydrogen bond will kind of depend on the covalent bond. Sometimes it's hydrogen to hydrogen, but we will cover that. But obviously, you can have a single covalent bond and you can have double covalent bond depending on how many you are sharing. And if these are two unequal sharing, I call it polar covalent. If it is equal sharing, I call it non-polar sharing. Is that okay so far?
Yeah.
So hydrogen with hydrogen, that will make a covalent bond. It's single covalent bond and it is non-polar, isn't it? It's non-polar. If I have one oxygen with two hydrogen, that's okay. But that's polar, right? Polar means leaning to one side versus the other. I have one pool to move toward. Just to understand where the name came from. Polar compounds. Okay? So now we have water attracted to another water, attracted to another water. And so all the water will come together because of that. Okay? Any oxygen and hydrogen from two molecules, they come together, and this will make the water and how the water stay together. So here it is. This is the hydrogen bond between hydrogen and oxygen. Hydrogen slightly positive, oxygen. This is exactly what I showed you here, right? So this is what's happening. And another molecule, another molecule. All of these molecules will come together and you're making the water molecule at the end. The hydrogen is the weakest one. And because of this hydrogen bond in the water, and is the water polar or non-polar? Polar. The whole water is molecules, and each molecule is unequal sharing. So the whole water is called polar, right? Hydrogen, is that polar or non-polar? Non-polar. Okay? So if that's the case, because of all these hydrogen bonds together, it will make the water come together and make the surface tough. Enough that you can put something on it and it doesn't drop, right? You can put something that's tiny and it will, like a fly or something, it will stay on the surface because of that cohesion that's happening there. The other thing is, still talking about the water, if you put an ice cube on the water, is it going to float or not?
Float, yes.
It's going to float. Try it. Get ice cube and put it in the... Or if you... Did you hear about these accidents that some people think it's just ice and they stepped on it and they got into the water underneath? It means the ice is floating on top of the water, right? So the thing is, why is the ice, which is another form of water, why is it floating? It's solid. You change the liquid to solid. I understand that. But the idea is why it is floating. Did you ever see pieces of ice floating on the surface of the water?
Yes.
Why is it is it floating? Because when you lower down the temperature to make it ice like this, these hydrogen bonds are going to become loose. They become loose, okay? So this will contain less amount of water. Believe it or not. If you get a cup and fill it with ice, let it to melt, it will not fill it anymore. It will be like 2/3, okay? Try it. So what is that? I see it like this. It should be the same as this. No, it is not. This ice is less water, contain less water. So why it is bigger size like this? Why it's big? Because when you cool it down, when you decrease the temperature, the hydrogen bonds become loose. Some of them breaks down. So these molecules move far away from each other. So even though you see it like this, but it actually contain this water. And that's how it floats. So you see it big like this, but it's not as heavy as the water underneath. It's lighter. Yes?
No, I wasn't sorry. I was
Ah,
just
okay. So water is a polar molecule, and you need to remember that. It's polar molecule. Okay? The hydrogen bond, I mentioned it's a very weak bond, right? So automatically know that you're looking at the water at this second, and you're looking at the water, know that the hydrogen bond are breaking and forming, not all of it. Okay, this part is breaking and then it's forming while this part is breaking. It happens all the time because it's weak enough. Okay? Break down and form again, break down and form again. Not all of it at the same time. Part and it kind of exchange. Water is extremely important, or it's considered the most important fluid on Earth for different reasons. Number one, it floats. Why that is good? Why, if water is frozen and it's ice, it floats? What's so good about this? Because under the ice, there is a lot of organisms right there, right? Like when it comes to the winter and it's getting really cold and you have ice. Do you know that there is fish and a lot of other organisms and underneath?
Yep.
They will still survive. They don't die, right?
Right.
If that was not the case, if that was not the characteristic of the water, that when it becomes snow, it floats. If that was not the case, it will not float. So it will go down, 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 down. The whole thing will be ice. Everything will die. Right? So it is important for life. The characteristic is important for life. This characteristic or this property of water, that it become lighter weight when it is ice. This is one. The other thing is, it's a very effective solvent. What do you mean by solvent? Solvent mean things are going to dissolve in it. Can you get salt and dissolve it in the water? You call the water, what do you call the water? Solvent. Okay, and what do you call the salt?
Dissolve.
The solute. And what do you call the whole thing?
Solution.
Solution. Right? Can I get sugar and do the same thing? Yes. I call the water solvent. I call the sugar the solute. You put ink in the water, everything will become blue, right? So it's dissolving, isn't it? You call the water solvent, and you call that ink the solute, and you call the whole thing, after you mix it, you call that a solution. So obviously water is a very effective solvent, and this is because another characteristic. So remember, one of the characteristics is when you cool it down enough to freezing point, it become ice, which is lighter weight and it floats, right? This is one. The other one is, we know that the water is polar, right? The water is polar. Because it's polar, if you put something else in it, it will dissolve. If that, like the water is polar, right? So different parts have positive here and negative here, not positive here. It's polar. So if you put something in it, it's going to dissolve. So why the water is a good solvent? Because it is polar. It's polar. Okay, so things can dissolve in that polar. The other thing is temperature regulation. They found that water resists temperature change. It takes time. Like put the water on the stove or on the it takes time, right? Because it's one of the characteristics of I'm talking about the characteristics of water that you have to know. Okay? Number one, we talked about the ice. Number two, we talked about it as solvent. Number three, temperature resistance. It resists temperature. It stores the energy in it. If you put heat, it will store it and it's not going to change much. It doesn't change that fast. It takes time for the water to boil, right? Don't like you heat it and it boils. It takes time. Why? Because it's one of the characteristics of water that it absorbs energy and does not change temperature that much. Absorb, keep, and does not change that much. So we call it resist or resistant to temperature change. Okay? And this is important for temperature regulation, like you have a lot of water inside your body, right?
Yes.
If that was not the case, you are going to, if this is getting cold, you're going to freeze. You don't freeze. Why? Thanks to the water, among other things. But the water is taking your heat, your energy, and keeping it for you. This is temperature regulation, isn't it? Yeah. Beside other things that we'll talk about. Number 4 is cohesion and adhesion. Because this is water molecule and another water molecule, they have hydrogen bond, they stay together, and another one, they all stay together, and we call that cohesion. Cohesion and adhesion, okay? And cohesion is why, if you ever see that, a mosquito can stay on the surface of the water, right?
Yeah.
Because of that surface tension that's coming from the cohesion of the different molecules. Okay? This is just what I already explained. Look how these are getting away from each other. Like if you count the molecules of water here and count here, this is less than this. Did you get the idea? Mm-hmm. Count the red here and count, don't really count. Just look at it. This is less than that, right? Why? Because the hydrogen bond is getting loose. So the molecules are moving away from each other, right? So in that same one, you have less molecules, and that's why it floats. So if I have a cube of ice and a cube of water, is it the same? Or if I get a cube of ice and I let it dissolve, is it going to be the same volume?
No.
No, it will become less. Okay? If you have a liter of ice, it will become maybe 3/4 of a liter of water. Do you know that? it get less. Okay. And did you understand the significance of each one of the 4 criteria that I talked about? Okay. So here is water as a solvent. You can dissolve a solute or an agent, a solute, and you make a solution out of it. And that's why water is biologically important solvent, the most important solvent, biologically important solvent. Okay, because it's a very good solvent. Why? Because it's polar. Okay, so we have a lot of things happening inside our body. We'll talk about it later. But for now, remember that because of this water inside our cells and inside everything, the blood is mainly water, the lymph is mainly water, and in your joints there is fluid that contain water. In your eye, it's everywhere, right? And it's a very good medium, so everything can go in there, dissolve for some time, and then you can take it back so it can transport, right? This is as a solvent. And I talked about the heat already. It absorb but resist change in temperature. Okay? And if you think about it, why Earth? The temperature on Earth is relatively, it's not exactly, but relatively stable. Like it gets colder and it gets hot, but to a limited extent, right? Why, for example, why doesn't, like, what's the maximum that you've seen here in America or in Michigan? Like 100, 110, maybe? Did you see it 200 before? Did you see it 500? Yes, you'll die, right? So why we can live on Earth? Because of the water. The water is the one that's making this. It is stabilizing. It is resisting the change. Did you understand the idea? So we have a lot of water, like all these oceans and and lakes and all of this water on Earth. This is what's stabilizing the temperature on Earth to a good extent. It's not 100%. It's not stable. It's not the same. But the range is too tiny enough for us we can survive, right? If you look at other planets or other parts that nobody survived there, you can go like from here to here, 500. How can you survive, right? Thanks to the water. We have a lot of water on Earth. The more water you have, the more stable temperature that we have. The other thing with water is sweat. When you sweat, isn't it? It's not water. It's mainly water, isn't it?
Yes.
Water and a couple of things dissolved in the water.
Salt.
Salt is the main one, but it's not the only one. Okay? Salt is the main one. All right? So what's happening here? Here it is. Right now it's too cold, right? It's cold. When it gets hot, you start to sweat. What's happening now? Here is what's happening. There is something called core body temperature, the temperature deep inside your body. And this is more hot than the outside. Meaning, there is a difference. If I put the thermometer here on your skin, it will give me a reading, and if I put it in your mouth, it will give me a different reading, right? The other way is to put it in the rectum. This is another way of doing it, which is deeper, right? And it will be more hot, right? So the deeper you go, the more heat it is. It's like we were talking about, like within 2%. It's not or 2 Fahrenheit. We're not talking about, or actually 2 degrees centigrade, like 3 or 4 Fahrenheit. We're not talking about huge difference, but it is different. Okay, it is different. So the blood is inside, deep inside, right? So the blood that's deep inside contain the highest amount of heat, right? It's hot, more hot inside. The temperature is higher deep than outside. The skin is the coldest part of your body, isn't it? It's exposed to the outside. So here's what's happening simply. The blood that's deep inside, that contain all of this heat, if it's getting hot, you see yourself getting like pinkish, reddish, right? Because the blood vessels dilate, so the blood goes out here. From deep inside, it goes out so you can get rid of the heat. This is one. The other thing is the sweat that I'm talking about right now, which is returning back to water. The sweat is going from inside to the outside, isn't it? So it is hot. It contains the heat and goes out, and when it goes out, you lose it, right? And then you get more water taking the heat from inside, take it to the skin from outside, evaporate. next, next, next. This is how you lose heat if it is really hot, and this is important to regulate your body temperature beside other things, including vasodilation. Vasodilation means your blood vessels dilate so that more blood go to the surface. Does that make sense or not? Biology should make sense. Okay? It should make sense. We need to understand.
Can you go the opposite way? Like if you're cold?
If you're cold, you cannot get the sweat back, so it doesn't go the other way around, but the blood vessels are going to constrict so that you do not lose the heat. You keep it for yourself. This is one. There are other things, including shivering, for example. Like if it's getting really cold, don't you go like shivering a little bit? When you shiver, the muscles are contracting and you're losing some heat or some energy in the form of heat. So you heat yourself by shivering. So there is another mechanism, but I'm talking about the importance of water as a regulator of the body temperature. Are we okay so far? I talked about the cohesion before. You can see something like this on the surface of the water because of cohesion. Cohesion, which is attraction between the molecules sticking together. Cohesion is what make the surface tension. So what's making the surface tension? Cohesion, which is the attraction between the water molecules. Is that okay?
Yeah.
And because of that surface tension, things can float on the water, something like this. It can actually stand on the water almost, right? Because of that surface tension that come from cohesion. Okay? Last thing here is the pH. Last thing that we're talking about today, which is the first part of this chapter. pH. The question is climate change, that a lot of people are saying it's a myth, it's a joke, it's not true, right? Climate change, it is science, it's a fact, right? So what do you think will happen to the ocean water, which is a question here? If the climate change happened, that they are denying, but it's actually happening, and it become more acidic, a lot of things will die, right?
Mm-hmm.
Because every single one of the organisms on Earth, they need a specific pH. pH, right? Acidic a little bit, alkaline a little bit. Every organism have its own optimum pH. When you change the pH, make it acidic or basic, they cannot survive. So what's happening here is all these factories, they are talking about right now specifically deregulation. Remove the regulation, right? Remove these laws, right? I'm not talking about politics. I'm just getting you to this idea that all these factories with everything evaporating and the carbon dioxide that's not controlled anymore, this everything here will ultimately, a good part of it will go down to the water, and the water become acidic. And when the water become acidic, we're actually losing. We can lose actually species. The whole species can be gone because of changing that. And why I'm saying acidic specifically? Because of the carbon dioxide. I don't know if you're familiar with that or not, but did you ever look at the soda machine, like you're getting a cup of Coke or Pepsi or whatever? Did you see that machine from the back? Like you look from the front only, looks nice, right?
Yeah.
You just take some ice, a couple of ice, and then get some Coke, and that's it, right? But did you look from the back? You didn't look from the back. If you look from the back, you will see the following. You will see two tubes coming from the back. One of them is bringing water, and the other one is bringing carbon dioxide. The other one is bringing carbon dioxide. And the machine itself will have that flavor, whatever it is, Coke or Sprite or whatever it is. So water come, and then the flavor come, and then carbon dioxide come under pressure. Under pressure. And when you put the carbon dioxide under pressure, it's going to dissolve in the water to make something called carbonic acid. And this is where the name carbonated beverages came from. Isn't the Coke and Pepsi and all that's called carbonated beverages? When you say carbonated, means you added carbon dioxide and you're creating carbonic acid. What's carbonic acid? Carbon dioxide and water. Under pressure. You don't just get some carbon dioxide and put it in the water.
Yeah.
It has to be some pressure, even a little bit. Okay? So why I'm mentioning that? Because this is what's actually happening. All this carbon dioxide, it will go ultimately dissolve in the ocean water, making carbonic acid. Isn't carbonic acid is acid? Carbonic acid is acid. So the ocean water and all the water ultimately become acidic if you just leave it like this? Yes. And this will cause a lot of disruption. Okay, so if we're talking about any aqueous solution, like water is one of the aqueous solutions. Aqueous solutions, translation, solution that contain mainly water, or that consists of mainly water. Is that clear? Aqueous solution is a solution that's mainly water. Okay? So this solution will have X amount of hydrogen, X amount of OH, and those two are making the acidity versus alkalinity or basic. If you have more hydrogen, you become acidic. If you have more hydroxide, you become alkaline or basic. Is that okay? So if it is neutral, if it is the pH is in the middle exactly, meaning hydrogen and hydroxide are equal. The amount are exactly the same, right? What if you have more hydrogen? What do you call it? Acidic. What if you have more hydroxide group?
Basic.
It's called basic, right? So this is what's determining if it's acidic or basic. The pH, when we measure it between 0, and this is the most acidic thing on Earth, and it goes all the way to 14, which is the most alkaline thing on Earth. And everything, any aqueous solution, any solution that we have would range from 0 to 14. What's exactly in the middle? 7. This is called a neutral. Is it acidic or alkaline? It's neutral. It's not acidic or alkaline. And this is only distilled, purified water. So practically speaking, we do not encounter anything that's neutral. You can find it in the lab. But even the water that I'm drinking, yes, it's not. It is not. The only thing on Earth that's neutral, like exactly, hydrogen and hydroxide group equal exactly. Neutral, 7, exactly 7, not 7.1, 7. This is only purified distilled water. Okay. Other than that, even the water that you drink from the water bottle or whatever you're drinking, it's not neutral. Okay. So pH will range from 0 to 14. Which one is the most acidic?
Purified.
0.
Most acidic, 0. Okay. Anything under 7 is acidic, red. Anything above 7, which is between 7 and 14, we call it alkaline. Okay, so look at these examples here. This is something that's not expected. Do you know that tomatoes is acidic?
Yes.
It is acidic. Lemon, for example. Battery is very acidic. The stomach, like 1, is 1 acidic or alkaline? Very acidic, right? Very acidic. 1 is that's close to 0. Okay, and if you go the other way around, you can something like ammonia, like household bleaches and lime and all that stuff, and that's why they always say keep it away from children, because it's as bad as acid. Okay, which one is worse, 14 or 0?
14. 0.
Both of them. Both of them. This is very bad and this is very bad. This is extreme and this is extreme. As long as you move away from 7, it's becoming alkaline or it's becoming acidic. Okay? And so on. You can take a look at this, but it's from 0 to 14. If it is 7 and I add hydrogen ions, what it will become?
Alkaline.
7 and I added hydrogen. It will become acidic. It will become acidic. Buffer. What's buffer? Buffer is something that we have in our body. Okay? Buffer is something, a system that we have inside our body, and this system is going to buffer the pH. What do you mean buffer it? Buffer it meaning make it closer to normal. Your normal, your blood, 7.4. Is that neutral or acidic or alkaline?
Alkaline.
Slightly alkaline. More than 7 is alkaline. Less than 7 is, don't ever forget this. 7.4, is that slightly acidic or slightly alkaline? This is your blood. So your blood is not neutral? No, it's not.
Should be 7.
It is not neutral. Your blood is not neutral. It's slightly alkaline. Okay? So what's happening here, the buffer is system inside our body, because practically speaking, you cannot keep it 7.4 24/7 for your entire life. That's impossible. You can't do that. You always add acids or remove acids. There is always dynamics and it's always change. But on the other hand, I have the buffer that's moving around all the time to make sure that it's returned back to normal. We call it buffered back to normal. What time are we supposed to finish? 50 or 40?
50.
50, you still have a couple of minutes. Okay, so this is the buffer system. And what's the buffer system? The buffer system is like this. I'm the buffer, okay? I have, on one side, I have weak acid. On the other side, I have weak alkali or base. I have both of them. And I'm moving around like this in the blood, okay? I'm moving around. And the blood somehow gained some hydrogen. It will become what? Acidic, right? Let's say, give an example, it becomes 7.3. This is moving toward acidic. That's not good. We have to keep it as it is. So I have two ends now, and I'm going using each end depending on the situation. In that situation, which one should I use? The acidic end or my alkaline end? My alkaline end, yes. And the alkali, by definition, or the base, is what's going to remove hydrogen out. So if you take that hydrogen out, you're returning back to 7.4, which is good. And this is what you need.
So the buffer is either acidic agent or alkaline agent?
It's both of them. I have two ends. Okay, I keep my two ends like this. Look, this is one end. I'm holding this. It's not opened. I close it like this, as acid. And here I have base. I didn't open it. I didn't use anything yet. So I will go around. Is it getting acidic? Yes. I open my base, and I will remove some hydrogen. How about, just 1 second, how about the other way around? It's for some reason, there are a lot of reasons and we'll talk about this, but what if it's getting alkaline for some reason, whatever the reason is? Which end should I use?
Your acidic.
I will open my acidic side, right? And I'm going to release hydrogen. The acid is what release hydrogen. The base or the alkaline is what remove hydrogen. You understand what's the buffer? So the buffer is going to buffer the pH back to normal. What's normal? 7.4. What is 7.5? Is that alkaline or acidic?
Alkaline.
Which one should I use? My weak acids. That's going to do what? How is going to do buffer? Releasing or taking out?
Taking out.
Releasing.
Releasing. It's getting basic. 7.5 is basic, isn't it?
Yeah.
So I wanted to make it more acidic, right? I'll use my acid end. So I'm going to release hydrogen. When you release hydrogen, you're acidic. What if it is getting 7.3? It is getting acidic. Which end should I use?
Alkaline.
The alkaline end, right? And what's the alkaline end is going to do? Take hydrogen out. Do you understand? What's your question?
So hydrogen ions, the more hydrogen ions, the more acidic, right?
Exactly. And the more hydroxide or less hydrogen, it's the same thing.
Okay.
Did you understand the idea? Like if you have perfect gray, equal black and white equally, that's perfect gray, metal, right? If you want to make it darker, there are two ways. I can add more black, or put less white, right? And the other way around, right? So it's relative. It's not exactly like this. Did you understand the idea? So am I going to remove hydrogen or add hydroxide group? I can do both of them. But practically speaking, you're dealing with hydrogen more, less or more. Okay. So if you're exercising, for example, if you exercise, you're adding something called lactic acid. Just for your information. If you're exercising too much, you're adding lactic acid. So that's moving the pH toward acidity. So the buffer will come, will say, okay, you're exercising and you're making your blood a little bit acidic, and I'm going to remove that acid from you. I'm going to use my base end or my basic end. I take off some of this hydrogen, it will return back 7.4, which is normal. I talked about carbon dioxide. When carbon dioxide dissolves with water, what does it make?
Carbonic acid.
Carbonic acid. So it makes acid? carbonic acid, which is an acid. Okay, and I talked about the effects of increased carbon dioxide on the ecosystem and on life on Earth. Okay, so this is for the first part of this chapter.